Welcome to Physics Corner, Motion, Secondary School Physics, Part 5, and the topics to be covered are equations of motion for a uniformly accelerated bodies. First relation is velocity-time relationship for constant acceleration. To understand this, let's consider the case of a body which is under uniform acceleration through velocity-time graph. We have already seen that the straight line in a velocity-time graph gives you constant acceleration. Let the initial velocity of the body be u, and as time progresses, the body must have attained a velocity capital V or small v after some time t. Hence, in this time t, the increase in velocity of the body is v minus u. To find acceleration, we should find the slope of the graph, which is given by v minus u over t. If you simplify this, that gives you v is equal to u plus a multiplied by t. Hence, the velocity-time relationship is given as final velocity is equal to initial velocity of the body plus constant acceleration multiplied by time taken to attain the final velocity. Let's go for the second relation, displacement-time relationship, and to understand this, let's again consider the velocity-time graph for constant acceleration. Let the initial velocity be u, and after some time let the velocity of the body be v after some time t. Hence the increase in velocity is given by v minus u. We already have understood that the area under velocity time graph gives displacement. Hence, total area under this particular graph, considering for a time t, is divided into two regions. One is a triangular region and the other is a rectangular region. Hence, total area is given by area of the rectangular region plus area of the triangular region. Total area is equal to displacement. Hence, displacement is equal to area of the rectangular region, which is obtained by the product of its length t and breadth u plus area of the triangular region half multiplied, since it is a right angled triangle, half multiplied by base, which is time t here, and height, which is given by v minus u. And by simplifying this using the relation v minus u is at, the very first relation, velocity time relation, that gives out to be displacement is equal to ut plus half a into t. So the final relation is s is equal to ut plus half a t square. So hence the displacement time relationship is given by displacement is equal to initial velocity multiplied by time taken plus half multiplied by acceleration times time squared. Initial velocity of the body, a is the constant acceleration of the body, and t is the time taken to cover a displacement of s units. Last and final relation, velocity displacement relation for constant acceleration. To understand this, let's again consider the same case, uniform accelerated body under velocity time graph, which shows you a straight line. We all know the area under the graph gives you displacement. Hence, here, instead of taking the area into two different parts, let's take into a single part as a trapezium. Here, if you observe, the shape under the graph looks like a trapezium with two parallel sides, one being the vertical line over here and the other being a dotted vertical line over here. So total area gives you area of the trapezium. So total area is displacement equal to half times area of trapezium is half times distance between the parallel sides, that is time taken t in this case, the distance between these two, this one parallel side 2, so distance between them is t, so t times sum of the parallel side. The one parallel side is u and other parallel side is v. That gives you displacement is distance between the parallel sides multiplied by sum of the parallel sides. Again, using the very first relation, for simplification we would get the final velocity displacement relationship as follows: v squared minus u squared is 2as. And the three equations of motion for uniform acceleration are: first one, velocity time relationship, v is equal to u plus at. Displacement time relationship, s is equal to ut plus half times at squared. Displacement velocity relationship or velocity displacement relationship, v squared minus u squared is 2as. If you would like to apply the same equations for uniform retardation cases, and then we have to replace the plus sign of acceleration with minus sign, because retardation is negative of acceleration. That gives you v is equal to u minus at, s is equal to ut minus half at squared, v squared minus u squared is minus 2as.